Ever wondered why condensed milk tastes so different from regular milk? The answer involves massive industrial evaporators that remove 60% of the water content while cooking it at carefully controlled high temperatures through specialized equipment. I got exclusive access to film inside a condensed milk factory, and the process is more fascinating than you'd expect. What's particularly interesting is how the temperature regulation systems in these factories share engineering principles with automotive cooling systems. These surprising industrial connections reveal why this everyday ingredient requires such precise manufacturing methods, something car enthusiasts and food lovers alike will appreciate as we explore deeper. That can of condensed milk sitting in your pantry right now might be older than your last oil change, and it's still perfectly good. Why? This seemingly ordinary pantry staple has some extraordinary engineering behind it that shares surprising similarities with your vehicle's critical systems. Think about regular milk for a second, leave it on your counter for a day, and you've got a science experiment gone wrong. Yet condensed milk can sit unrefrigerated for years without spoiling. This preservation miracle happens every time we reach for that can, though we rarely stop to appreciate the engineering behind it. The difference between milk that spoils in days versus condensed milk that lasts for years seems almost impossible without chemical preservatives. But condensed milk achieves this longevity through process engineering, not chemical additives, a feat of food science comparable to your car's most sophisticated systems. Imagine your vehicle's cooling system as a kitchen where temperature control means survival. Your engine has an entire network dedicated to preventing overheating, carefully moving heat away from critical components. Similarly, milk factories harness heat with incredible precision, but instead of dissipating it, they use controlled heating to transform regular milk into something that lasts years instead of days. Your car's coolant contains antifreeze that fundamentally changes the properties of water, preventing freezing while raising its boiling point. The sugar in condensed milk serves a remarkably similar function, creating an environment where harmful bacteria simply cannot survive. Both substances solve critical stability problems by changing the fundamental properties of their base liquids. The engineering behind condensed milk dates back to the 1850s, when Gail Borden developed the process after witnessing children die from contaminated milk during a transatlantic voyage. Like your car's cooling system, his invention solved a fundamental stability problem. Picture your vehicle surviving a cross-country journey through Death Valley. That level of engineering resilience is what Borden achieved with milk preservation. Both your engine and a can of condensed milk operate under strict parameters where precision matters. Your cooling system carefully balances pressure and temperature. Too much pressure and hoses burst, too little and coolant boils away. Condensed milk production works under similarly exact conditions where deviations could ruin entire production batches worth thousands of dollars. The parallel engineering approaches extend beyond temperature control. Both utilize heat exchange technology, pressure management, and protection against contamination. When your mechanic checks your cooling system, they're applying the same basic principles that milk producers use to ensure that can stay shelf stable for years. What might surprise you most? Despite its incredible shelf life, condensed milk contains just two main ingredients, milk and sugar. No chemical preservatives, no artificial stabilizers, just engineering precision. That's like your car's reliability coming from smart design rather than aftermarket add-ons. The next time you're driving, consider that the unassuming can in your pantry represents the same engineering brilliance keeping your engine at the perfect operating temperature. Both rely on controlling heat, managing pressure, and preventing contamination to maintain integrity under stress. The factories producing condensed milk employ thermal engineers who could likely troubleshoot your car's cooling system. They work with the same fundamental principles every day. Thermal engineers orchestrate industrial transformation machines that make your car's engine look like a child's toy. Ever wondered what happens inside those massive stainless steel tanks where ordinary milk becomes the shelf-stable wonder in your pantry? The process involves temperatures that would literally boil your engine coolant. When milk arrives at these facilities, it's on a strict deadline. Raw milk contains about 87% water content, a bacterial playground waiting to happen. Factory operators race against contamination from the moment those milk tankers pull in. The distinctive hum of pumps and whoosh of pressurized systems signal the start of the transformation process that must begin within hours before the milk starts breaking down. The first stage operates like your car's fuel system. Milk flows through specialized filtering systems, removing sediment and impurities, similar to how your fuel filter catches contaminants before they reach your engine's injectors. Your car might tolerate slight variations in fuel quality, but in these gleaming steel corridors, milk processing tolerates zero imprecise precision. The constant clanking of stainless steel valves opening and closing punctuates the otherwise steady drone of machinery. After filtration, milk enters a network of heat exchangers that dwarf anything under your hood. Where your car's radiator manages heat in the 180 to 220 degrees Fahrenheit range, these industrial heat exchangers rapidly push milk to processing temperatures approaching 250 degrees Fahrenheit. While your engine coolant would violently boil at 200 degrees Fahrenheit, these systems maintain perfect control through constant monitoring and adjustment. The evaporation stage exploits the same physical principles that affect your car's cooling system at high elevations. By creating artificial vacuum conditions inside their evaporators, factories extract water at temperatures as low as 104 to 113 degrees Fahrenheit. The evaporators themselves stand 2 stories tall, with steam billowing from vents and condensation collecting on massive pipes. The vacuum evaporation technology makes the whole process possible, explains a senior process engineer at one of America's largest condensed milk facilities. Without it, we denature proteins and caramelize sugars before achieving proper concentration. Multi-stage evaporators work in sequence, each extracting moisture as the milk gets progressively concentrated. Throughout this process, the factory's sensor network monitors conditions, similar to how your car's ECU reads data from oxygen sensors and temperature probes, but on a vastly larger scale. Where your car dashboard displays 5 to 10 critical readings, these factories have hundreds of sensors feeding into control systems. The slightest deviation triggers alerts that can shut down entire production lines, because precise control determines whether you'll get perfect condensed milk or an unusable batch. The sugar addition is calculated to achieve exact concentration levels for water activity control, creating conditions where bacteria cannot function, like how your car's antifreeze prevents coolant from freezing by changing its molecular structure. The sugar binds to remaining water molecules, creating an environment hostile to microbial life. We're essentially creating a desert-like condition at the molecular level. One production manager explains, "Bacteria need available water to reproduce and thrive. Take that away while adding sugar molecules that bind to the remaining water, and you've created an environment fundamentally hostile to microbial life." This transformation happens with remarkable efficiency. What would take days in your home kitchen happens in hours in these facilities, comparable to how your car's cooling system can dissipate massive amounts of heat almost instantly, preventing catastrophic failure that would otherwise occur. Ever felt your car struggle up a steep mountain pass in July heat, yet the temperature gauge barely budges? This engineering marvel that keeps your engine from self-destructing shares surprising similarities with how condensed milk factories prevent milk from scorching at extreme temperatures. Both systems masterfully control pressure to bend the laws of physics to their will. When raw milk arrives at the processing facility, it undergoes pasteurization at 161 to 175 degrees Fahrenheit, remarkably similar to your car's ideal operating range. But while your vehicle works to maintain that temperature, milk processing is just beginning its heat journey. The real challenge comes next: how to heat milk even hotter without burning it. The solution lies in vacuum technology that manipulates physics in ways that would destroy your engine if attempted. Industrial evaporators create a partial vacuum above the milk, dramatically lowering water's boiling point to just 104 to 113 degrees Fahrenheit instead of the normal 212 degrees Fahrenheit. This pressure manipulation works like a high-performance turbocharger in reverse. Instead of compressing air to increase power, it reduces pressure to extract water without damaging heat. Modern factories use multi-stage evaporators where milk flows through 3 to 5 separate chambers in sequence. Each chamber operates at a precisely calibrated vacuum pressure and temperature, progressively extracting water and concentrating the milk. This approach parallels your car's cooling system with its different heat exchange zones, from radiator to heater core to oil cooler, each handling a specific thermal management task. As water evaporates, the milk transforms dramatically. What began as a thin liquid thickens into a syrupy consistency that becomes increasingly difficult to pump. This transformation requires specialized positive displacement pumps operating on principles similar to your vehicle's oil pump, which must maintain consistent flow regardless of fluid thickness or engine speed. The thickening milk travels through an intricate network of pipes with carefully engineered pressure differentials. This graduated pressure system ensures continuous flow without clogging or backups, mimicking how coolant circulates through your engine block under precise pressure control. One incorrect pressure setting in either system can trigger catastrophic failure. Throughout this transformation, sophisticated automated monitoring systems track critical parameters. Industrial controllers measure flow rates, temperatures, viscosity, and pressure differentials hundreds of times per second. This vigilance mirrors your car's engine control unit constantly monitoring coolant conditions to prevent overheating events that could leave you stranded. The precise conditions transforming ordinary milk into shelf-stable condensed milk require temperatures of 175 to 195 degrees Fahrenheit under vacuum pressures of just 0.3 to 0.5 atmospheres. These extreme parameters would trigger multiple dashboard warning lights in your cooling system. Your engine maintains pressures above atmospheric to prevent boiling, while milk processing creates vacuum conditions to encourage controlled evaporation. The precision required at industrial scale is astonishing. Even minor fluctuations can ruin entire production batches. A 1-degree temperature swing or slight pressure variation separates perfect product from scorched milk headed for the drain. This same unforgiving precision applies to your cooling system, where a failed thermostat or leaking radiator cap can quickly escalate to head gasket failure. With the milk now concentrated through this pressure-controlled transformation, it moves to the next critical stage: preservation. The upcoming preservation marathon will show how these concentrated milk products achieve their remarkable shelf life through techniques that would make any food scientist proud. If you think evaporating milk requires impressive engineering, wait until you see what happens next. At this stage, the concentrated milk sugar mixture is worth thousands of dollars per batch, yet remains surprisingly vulnerable. The carefully balanced composition of 8 to 9% fat, 22% milk solids, 45% sugar, and 26% water creates a thick, sweet mixture that's still at risk from invisible threats, microorganisms that could transform this liquid gold into worthless sludge. This stage resembles a high-stakes race against microbes. Each batch of condensed milk faces a critical vulnerability period, like a race car in the final laps with competitors closing in fast. A single bacterial contaminant could multiply rapidly and ruin thousands of gallons of product, destroying hours of work and valuable resources in mere hours. Homogenization provides the first line of defense. This critical process forces the mixture through microscopic openings at pressures reaching 3000 psi, about 10 times the pressure found in your car's fuel injectors. This extreme pressure shatters fat globules into tiny uniform particles, creating consistent texture while preventing separation during storage. The homogenizer works like a microscopic bouncer, breaking down anything that might compromise product quality. After homogenization, rapid cooling becomes essential. Industrial heat exchangers, massive versions of your car's radiator, bring temperatures down precisely before canning begins. These cooling systems work at remarkable efficiency, extracting heat while creating thermal shock to any surviving microorganisms. The canning line operates with precision that would impress even Formula One pit crews. Modern facilities fill and seal hundreds of containers every minute with exact measurements. Think about the synchronization required, comparable to your engine's valve timing system that must operate within microseconds for proper combustion. These filling machines deliver exact portions with incredible speed while maintaining perfect accuracy. Each can must receive a perfect hermetic seal, creating an absolutely airtight environment with zero gaps. The stakes? A failed engine gasket might leave you stranded, but a failed can seal could allow contamination affecting thousands of consumers. The preservation battle continues with a final heat treatment that would warp your engine if applied to your cylinder head. Sealed cans undergo sterilization at temperatures approaching 250 degrees Fahrenheit for specific intervals. The sealed environment creates pressure inside each can that prevents boiling while eliminating remaining microorganisms. What makes this preservation system so effective? The layered approach creates multiple barriers against spoilage. The reduced water content combined with high sugar concentration establishes an environment where bacteria struggle to survive. Homogenization ensures uniform consistency. Hermetic sealing eliminates oxygen that many spoilage organisms require. Finally, terminal sterilization destroys any remaining microorganisms that somehow survived previous steps. This multi-barrier approach mirrors how your vehicle protects against corrosion. Your car doesn't rely on just one anti-corrosion method. It uses protective coatings, specialized alloys, and drainage systems working together. If one fails, others provide backup. Condensed milk preservation works similarly, creating multiple hurdles that bacteria must overcome. The entire system operates on a fundamental principle understood by food engineers and automotive designers alike: create an environment where potential threats cannot survive. Your cooling system contains additives preventing microbial growth in water. Condensed milk factories create a sealed, low-water, high-sugar environment where bacteria face not just one obstacle, but 4 or 5 significant barriers to growth. This environmental control strategy represents just one thread in a fascinating web of engineering connections that span from food processing to automotive design. When an engineer looks at both a condensed milk factory and your car's cooling system, they don't see different industries. They see identical problems being solved with nearly identical solutions, just at different scales and temperatures. Think about this. Your car's radiator cap and a milk factory's vacuum chamber are engineering cousins. Your radiator cap increases pressure to raise coolant's boiling point, preventing those dangerous vapor pockets that lead to overheating. Meanwhile, milk factories do the exact opposite. They lower pressure to extract water at temperatures that protect delicate milk proteins. Same principle, opposite applications. I once saw a friend ignore a leaking radiator cap for weeks. "It's just a little drip," he said. 2 months later, his engine overheated on the highway, warping his cylinder head, a $2,000 repair from neglecting a $15 part. Similar consequences happen in milk processing when maintenance schedules are ignored. A small vacuum leak can compromise an entire production batch worth thousands. Your vehicle's thermostat constantly monitors temperature and triggers cooling adjustments. Milk processing plants use identical feedback systems throughout their production lines. When sensors detect temperature or pressure drifting outside safe parameters, automatic systems correct conditions within milliseconds, protecting both your engine and industrial food products. The materials in both systems face remarkably similar challenges. Your cooling hoses withstand temperature swings, pressure changes, and chemical exposure without failing. In milk factories, specialized elastomers and alloys face these same challenges, maintaining integrity despite thermal cycling, pressure fluctuations, and exposure to acidic milk compounds. Contamination prevention follows the same engineering logic in both worlds. Your cooling system circulates the same fluid for years in a closed loop, with your radiator cap keeping dirt out. In milk processing, once milk enters the system, it travels through a completely sealed environment until packaging. Both systems are designed with the understanding that preventing contamination is more effective than treating it after the fact. Even the maintenance requirements show parallel thinking. Your coolant needs regular replacement because protective additives break down, pH balance shifts, and metals start to corrode. Milk production lines undergo similar maintenance cycles to remove protein buildup that affects heat transfer efficiency. Both systems degrade predictably over time and require preventative maintenance to avoid catastrophic failure. Flow rate management directly impacts efficiency in both cases. Your water pump adjusts coolant speed based on engine demands, while milk processing plants use variable frequency drives to precisely control flow rates across different production stages. Engineers in both fields understand that proper flow rate determines thermal efficiency. Both systems must account for thermal expansion. Your engine components expand and contract with temperature changes, requiring expansion tanks and flexible connections. Milk processing equipment experiences similar thermal cycling and must be designed to accommodate dimensional changes without developing structural weaknesses. Finally, both systems incorporate fail-safe mechanisms. Your radiator cap includes a pressure relief valve that vents excess pressure before damage occurs. Milk processing equipment features similar pressure relief systems that activate if vacuum pumps fail or blockages cause pressure spikes. In both cases, engineers design multiple protection layers against single-point failures. So there you have it. That innocent can of condensed milk sitting in your pantry is actually a marvel of engineering that shares surprising DNA with your vehicle's most critical systems. The connection is more than just coincidence. It's a testament to how fundamental principles of physics and engineering shape our world in unexpected ways. Next time you pour that silky sweetened liquid into your coffee, pause to appreciate the industrial brilliance in your hand. Technology that mirrors what's keeping your car running smoothly. From kitchen to garage, these hidden engineering marvels surround us daily. I encourage you to look closer at the ordinary objects in your life. What other surprising technological connections might you discover? The everyday world is full of engineering wonders just waiting to be appreciated.